I equals I naught exp minus alpha into x. That is, suppose this is my material. I am discretizing the material into different nanometric energy levels or nanometric levels. So when the light falls on it, so this is the incident intensity I naught. So this intensity I naught is being absorbed by this particular layer, and the remaining light is transmitted to the next layer. So like that. So similarly in this layer also certain amount of light is absorbed. It is being transmitted to the next layer. So what happens is, so when the light gets absorbed, so you have an atomic layer. So in the case of atom, so we all know that there is a proton, neutron at the center, and then there is an electron which orbits. So when the light falls on it, so it tries to tap the electron. So when it tries to trap the electron, so we all know an atom cannot be to its stable state. So when it tries to come back to its stable state, it has to release certain amount of energy to come back to its stable state. So that is what it is trying to do over here. So what does it does is, so it will release certain amount of heat. So basically whatever absorption, so whatever absorption is there, so that absorption is appropriately translated in the form of heat. So that is what your light is used for, some kind of material processing or some kind of manipulation kind of arrangement. In fact, one example which I told you is like manipulating a cell. So in the case of cell manipulation, what normally we used to do is, so we used to fix up the light so that the light falls within a particular wavelength, it holds it and it can be used for manipulation. Okay, so in this case, the absorption of the material plays a major role. Another aspect is you use a light for different measurement techniques. So one measurement which I would like to say is like you can directly use a light for a measurement, or the other way is you can use a light shadow for a measurement. Okay, that is, shadow is nothing but your image, what you are getting. So basically you can employ a certain amount of image processing technique. Like, so this is one good example where you are using a light as a shadow. So with respect to the shadow, what you do is, you have a source, you have a wavelength selector, and you have a sample holder, and you have a detector. So you are trying to pick up your shadow, and from that shadow you are trying to capture the image. Okay, and then you are trying to analyze your image using different concepts such as image enhancement, image restoration, image compression, image coding, etc. So based on that, you are trying to analyze its capability. Okay, so as far as this image acquisition is concerned, so there are wide varieties of image acquisition which are available. So one example is something like where based on your what I would say, based on your requirement, you can go for image acquisition. For example, so I'm a person, I'm interested towards heat transfer characteristics. So in that case, what I will do, I will go for a IR region, so that with respect to an IR region, I can capture the heat profiles, and with respect to the heat profiles, I can somehow validate my overall structural requirement. So that is one example. So in all these cases, your camera and your image processing plays a major role. So where you have your image acquisition, which comes into the picture. So there are wide varieties of techniques which are available, which we call as shadowgraphy technique. So in fact, I can just give you an overview about the shadowgraphy technique, like and as well as the overall construction about the system. Now I am going into the whiteboard. Hope you could able to see my whiteboard. Okay, so let us take two different cases. One case is using a light. I am trying to monitor an in-situ temperature condition. That is, for example, I have a welding. So this is my sample. And I have a weld bead over here. So through this weld bead, I want to measure the temperature of this weld bead. Normally what we people used to do, so we used to put a thermocouple on this and you try to measure it. But there is one option is there, which we called, it's on a very good phase, which has a direct relevance towards optomechatronic systems, because which we call it as time resolved reflectivity technique. So in this time resolved reflectivity, what we do is we use a laser to hit on the surface, and the beam is collected using a detector. Okay, so what I'm doing is, so this detector is connected to an oscilloscope, so that through this oscilloscope you can monitor the variation which is happening on the surface. So what happens is, this is your laser. So this laser is a low power laser. So low power laser means like one which you use it for your pointer application. So in this pointer application, what normally you used to do is, so when the laser falls on it, so there will be a reflection. Obviously, there is not going to be a transmission, but there is going to be a reflection. So when a reflection happens, like for example, you have a molten surface. When the molten surface is a bit shiny, you have a high amount of reflection. And that reflection is well connected using a detector. And from the detector, it is fed to an oscilloscope. So from the oscilloscope, you can capture the signal, how much is the difference which you are getting out of it. Okay, so this time resolved reflectivity, so it can give me an overall picture with respect to time and with respect to percentage reflection, or I would say with respect to position or with respect to percentage reflection. The higher would be the liquid phase. The higher would be the reflection. So with respect to your reflection, you can correlate your temperature. Okay, so this is an interesting aspect with respect to your time resolved reflectivity. Now, how you tune your system basically takes care of your overall arrangement. So what normally people used to do is, they used to have a detector. These detectors are well synchronized in such a way that you get it in a pulse mode, and based on the pulse mode, you can just fix up your system. Okay, so this is one arrangement where you are trying to measure the temperature. Another one arrangement is there, which we called as shadowgraphic technique. So as far as in the shadowgraphic technique is concerned, like for example, you might have seen an engine. Okay, so this is an engine where there is a sparking which is happening because of the spark plug. Now, I would like to visualize how this sparking happens. So one option what I can do is, I can just use the laser. So this laser in the form of a sheet. Let's change this color. In the form of a sheet. And then I keep my CCD camera over here. So it's a integrated charge coupled device camera. So basically it's a high speed camera. So what does it does is basically, so when there is a sparking which is happening, so from the sparking, so you're trying to capture the shadow using this ICCD camera. So the interesting part in this is, when you try to capture the shadow from this ICCD camera, so you can see how your shadow behaves. Like for example, your shadow would be something like this, where it is something like you are having a light, and then there is something obstructing your light, and then you are trying to collect your shadow using a ICCD system. So you can one option is, you can go for a different pulse delay. So by changing the different pulse delay, it has a capability to fix the overall modulation which is happening. Okay, so this is one arrangement which we called as shadow graph. Another one system with respect to optomechatronics point of view, we call it as interferometric technique. I'm not sure how many of you are aware about this interferometric technique. So this, as far as this interferometry is concerned, as the name interferometry suggests, it is something like interface of the light. Basically, a superposition of the light is called as an interferometry principle. Okay, let me just give you an example. So the basic interferometry which we are going to discuss today is called as Michelson's interferometer. Okay, so the construction of the interferometer is something like this. I have a laser. From the laser, I have a beam splitter. This is my mirror M1 and this is my mirror M2. So what happens is when the laser falls on it, so this we call it as beam splitter. This splits the beam into two. So one, it is splitted and it is moving towards the mirror M1. The other is splitted and it is moving towards the mirror M2. So because of the back reflection from the mirror M2, it moves back. It moves back. Finally, it falls on the surface, forming such kind of interference pattern. So if we have a closer view of this interference pattern, so this interference pattern has alternate dark and white fringes. Okay, so like for example, it depends upon the color. For example, if I'm using a laser which is pinkish in color, so you will be having an alternate pink and a black. In case if I am using a white light, so which we called as a white light interferometer, where you have a patches of white and black which is coming out of it. Now, what I'm doing is I'm just keeping this mirror M1 as fixed, and then this mirror M2 as movable. So movable in the sense I am moving this mirror back and forth. So when I try to move the mirror, so obviously there is going to be a change in fringe. So this fringe is well connected using a photodiode. So using this photodiode, I am trying to capture the amount of variation coming out of it. So with respect to the amount of variation, so you can study the displacement which is happening in this movable mirror. Now, let me just give you an example. I have a material. I want to measure, I am just heating this material. I want to measure the temperature which is being incident on the material. So what I can do, since I already have a setup over here. So I'm in this mirror M2, I'm just fixing up my material and I am just supplying a heat to the material. So when I am supplying a heat to the material, there will be a kind of expansion which happens on this material, which will push the mirror in a forward direction. So which internally gives me, so it acts as a system where a heat is supplied. From the heat, there is an elongation is there. From the elongation, mirror is moving. And from the mirror movement, fringe pattern changes. So the interesting part in this is, so you are using a light which is in the order of few nanometer wavelength. So when the light is in the order of few nanometer wavelength, so obviously it has a capability to go for a high precise system. Okay, so how much ever heat is supplied, so it is being translated in terms of elongation, so that you can easily calibrate in such a way that how much with respect to the temperature, you can estimate how much is your variation in fringe pattern which is happening. Okay, so this is a very good setup. In fact, faculty should can demonstrate this setup in their laboratory at a very low cost. So only thing is a beam splitter will be costing around some 350, 400 rupees. A laser diode will cost something around 150 rupees and some two mirrors. So with that, you can ask your student to align so that you can see how the fringes are getting coming up. In fact, this is a very good system which has a capability towards measuring your pressure, measuring your temperature, even measuring your continuously monitoring your vibration. Like one experiment which we did in our lab. So we had a small pressure vessel. So in this pressure vessel, we kept two different mirrors and this system was kept over here. So that what happens is by just pumping the pressure inside, this entire system was getting elongated. So when the entire system was getting elongated, so obviously it will give certain amount of deflection on the surface. And with respect to the deflection, you can see movement, the mirror gets displaced, which has its own repercussion towards the variation in the interferometer, and which also gives me a better clarity about how much is the pressure which is being built on this surface. Okay, so this is one important aspect with respect to this microsource interferometer. In fact, these interferometers are further extended for different other applications for some kind of measurements as well as for other kind of other applications also. Okay, now we will, as an extension of this, now we will talk about one of the important aspects. So that is, these interferometers have a potential application towards different micro actuation systems. So one micro actuation systems which I would like to talk about is, like, for example, I have a smart actuator which is available over here, and then I'm just coupling this with a Michelsen's interferometer. So by coupling it with Michelsen's interferometer and by actuating it, so what happens is you can just study the displacement, the actuation performance, and the response to the actuator. Okay, so these are some of the different characteristics which gives me a better clarity about a Michelsen's interferometer. Next, one of the important component which is available in your purview is this one, an optical fiber. Okay, in fact, I think I will just go presentation. Okay, I think you could able to see my presentation. This frame grabber. We can see. Okay, so this frame grabber is one of the important aspects with respect to optomechatronic system, because frame grabber will be highly helpful for me to grab the sequence based on the requirement. So basically, it will be highly helpful for me to cater my requirement with respect to a sensitivity of the system. So this is a kind of image segmentation. I will directly go to some of the elements which are available. So one element is something like this. Okay, so this is called as a monochromator. So the main objective of this monochromator is, so these are some of the different elements which are available for optomechatronic applications. So the main objective of monochromator is, this monochromator has some kind of diffraction grating in it. So this diffraction grating will be highly helpful for me to select my system for a particular wavelength. Okay, so that is one major advantage of these typical monochromatic or monochromatic design. So this monochromatic design will move back and forth, so that this monochromatic design will be highly helpful for me to filter out my system. Okay. Another one is with respect to photo tubes. These photo tubes or photo multiplier tubes are interesting components. Basically, this will be highly helpful to narrow down the selection of the wavelength. Basically, these photomultiplier tubes comes under the category of detector-based system. So this is the overall construction of this photomultiplier tubes. So in this photomultiplier tube, for example, you are using a light for some kind of measurement. But unfortunately, when your light intensity is very less, so what you can do is you can just flip it up into these diodes. So these diodes play a major role in improving the intensity of the light. Okay, so that is one of the main key functionality of such kind of photomultiplier tubes. Okay, and next you might have heard about the silicon photodiodes. So silicon photodiodes works almost in the same principle. Basically, it has, as the name suggests, it has a diode in it. So in this diode, when the light falls on it, so it will be highly helpful for me to energize the system. So these silicon photodiodes are used for different applications. So one application is something like this. So where if I want to, in a mechatronic system or in some kind of system where you want to count the number of what do you call it, objects which are moving. So in those conditions, you will be having a light source and you will be having a photodiode. Necessarily, it might not be required that my light source should be on a visible spectrum. Even I can go for a IR spectrum so that it can be an invisible spectrum. So whenever the light gets cuts off, from that you have a photodiode which is being connected to a counter where you can grab the amount of cutoff which is being. So the next one is, this is a highly advanced system which we call it as a LiDAR system. So this LiDAR system is used in some kind of automotive system. Basically, these automechatronics are currently being employed efficiently in autotronic systems. So in this LiDAR system, what you will have is basically it is to maintain the gap between two different cars, okay, two different vehicles. So in case if there is a sudden break, so you will be continuously feeding a light and you will be getting a reflection back. Whenever there is a reduction in the distance, automatically the brakes are applied so that it can be used for avoiding the collision. Okay, so here you have a timer and a laser diode as well as a photodiode which is available, which is being continuously being monitored. And with respect to the continuous monitor, you can capture the distance between the two different ones. Okay, next is with respect to photoresistor. So the main advantage of this photoresistor is, so as the name suggests that, so when the light falls on it, the resistance gets changed. But it has its own limitation. It is limited only to a low level of intensity. So when there is a low level of intensity is there, appropriately you can just capture the signal. Okay, so it has its own application towards sensing the minute lights, or even it is used for measuring if you have a change in displacement with respect, and LDR can be used. Okay, next one is about an optical encoder. So this optical encoder is basically meant for measuring the angular velocity in any kind of system. So angular velocity means, like for example, I have a rotary disc. So in this rotary disc, I have a different slots which is available. So I have a laser source and a detector. So what I'm doing is, so based on the rotation of this disc, you can just calculate your RPM, because this has different slots. So when it tries to cut off the light, from that you can capture what is the RPM at which it is rotating, and this will give me a better clarity about the even on a micron level displacement can be easily measured using this optical encoders. And this is an example of a linear encoder. So the same principle where on a linear level you are trying to pitch into it. Okay, so this is, we call it as grating. So the main function of this grating is, so you have a line, in this line you have different markings which is available. So the grating will give you flexibility of selecting your wavelength based on your requirement. Okay, the most important advanced aspect with respect to optomechatronic system is an optical fiber. So usage of an optical fiber has its own advantage. In fact, I will give you a recent case study where currently people are employing optical fiber inside additive manufacturing component. The reason is, so by integrating an optical fiber inside an additive manufacturing component, so you can study the strain variation, and in fact it can be used to investigate the stress involved in it as well as the other aspects involved. Okay, so optical fiber has its own advantages towards diagnosing the behavior. Okay, so there are wide varieties of applications of optical fiber. So so optical fiber, basically fundamentally it has a core and a clad. So through the core and the clad, so you have a multiple reflection. So the bending or the strain in the optical fiber can be appropriately translated, and from that you can do the measure. Okay, so let me just show you some example where optical fibers are directly employed. So in this case, so this is your environmental signal, and this is your input through which a light source is being fed into it, and this is your light detector. So this light detector will be helpful for me to capture this. So now what I'm doing is, I have an environmental signal where it is being piled up into it. So I'm just giving a strain to it. So when I try to apply a strain, so based on the strain, you can just detect the light. Okay. Similarly, this is a kind of an intrinsic sensor. So like for example, this can be used for sensing the micro bending. That is, your pressure is translated to the micro bending, and it is further translated to a fiber, so that from that fiber you can study how much is the deviation which you are getting. Okay, so this is one good example where even you can study the vibration, as well as you can also study the micro level deflection which is happening on the optical fiber. So an advanced level of it is, people have tried to integrate some kind of grating into it. So when you try to integrate a certain amount of grating, so there is a chance that you can just shift your wavelength. So when you try to shift your wavelength appropriately, you can improve the sensitivity of it. So that is one aspect with respect to an optical fiber based grating. So in fact, this characteristics will give you a better clarity. So your incident beam is a kind of a flat top beam, whereas your reflected beam, you have two different gains. And in the transmitted beam, you can appropriately vary the system. Okay, so good part of it is you are trying to discretize your wavelength. So when you try to discretize your wavelength, your sensitivity level gets improved. Okay, so this is one example of a microbending sensor where you have a liquid which is available. Your liquid is filled. So based on the liquid level, a kind of force is being exerted on the optical fiber. So when the force is exerted on the optical fiber, there is a deflection which is happening, and that deflection is being efficiently measured. Okay, this is an interesting thing for a liquid level sensor. So you have a LED and you have a photodetector, and there is a reflecting probe over here. So with respect to your float, so this move back and forth. So when this moves back and forth, so your LED and the photodetector will act as a sensing medium to sense the float in a precise way. In fact, this is a very good system for diagnosing the fiber optic beam. Okay, so this is an advanced level where you have a chemical mixture. So through this chemical mixture, the chemical mixture is made to flow through the flow cell, and here you have an optical fiber, which is through which a light is made to pass through it. So the light moves in this direction and it gets reflected back. So when it tries to reflect it back, there will be two different kinds of phenomena which happens. One is obviously the reflection, and the other one is with respect to an intensity absorption. So in the case of intensity absorption is concerned, so your light gets absorbed. So when the light gets absorbed, so there will be a drastic change in the intensity. So with respect to a drastic change in the intensity, you can measure the signal in your PMT. So this is a kind of arrangement where a mechanical force is being applied. So you have a applied force which is there, and you have a decoupler, and this is your photodetector, and this is your mirror through which the light is falling and it is passing by. So you have your light source. This is similar to your beam splitter. So from this beam splitter, beam is splitted and it is diverted back to the photodetector. And from this photodetector, you are trying to sense your system. Okay, so this is one good example where your optical sensor is used for continuous monitoring of a level as well as the temperature of a storage tank. Okay. So these are some of the example. So this is one arrangement where optical fiber is used for sensing the strain in a railway track. So so beneath the railway track, you can just keep these optical fibers which are well mounted so that you can see the strain as well as you can continuously monitor the vibration using this optical fiber system. So this is one reference which I would like to show, so which has gained the Nobel Prize. So this is a kind of an optical tweezer. So in this optical tweezer, a light is being used for manipulating as well. In fact, this is the study which has got a Nobel Prize. Okay. So with this, I am closing my lecture related to optomechatronics system. So before closing my lecture, I would like to show you a small video about some of the aspects which we are performing in our laboratory. Okay, so in which there will be some aspects related to optomechatronics system also, where I can just explain. Could you able to see the video?
Yes, sir. Yes, sir. Yeah, okay. The voice is not there, sir.
No, video, this is not there. Audio is not there, only for some particular experts. Audio will do. So these are some of the facilities which we have. So we work on thin film and deposition, etc. So we have a E-beam evaporator, then we have a flash evaporation. So apart from that, we have some material characterization facilities available within my purview. So we also work on mechatronics training. So we have a control system unit as well as a strong pneumatic platform. So this is a wire arc additive manufacturing which we have developed in our lab. It is an in-house developed machine, basically for printing smart actuators. So this machine has a capability to build 30 centimeter by 30 centimeters sphere. Okay, so using wire arc additive, so we get the NIDA wires and we feed it on the. In fact, it has a capability to align your microstructure based on the requirement. Currently, we have sold this machine from IIT Indore to some private colleges also at a cheaper price, because conventionally these machines are in 50 crores, so we are selling it in less than 10 lakhs. It's a kind of technology transfer based systems. Okay. So this is This is a shape memory alloy structure. So which we have demonstrated at our IIT. So basically, shape memory alloy welding is a challenging task. So we have used a friction stir welding to weld a shape memory alloy structure. And this is a kind of study which we have performed in our lab. So this is a laser displacement sensor. Using a laser displacement sensor, we are trying to look into the life cycle behavior of the welded structure. So we go up to 1 lakh cycles and see how the breakage of it. So this is one good example of an optomechatronic system. So shape memory alloy gets actuated with respect to light, heat. So we thought that we will use a laser. This is one of the consultancy projects which we did for a company for making some kind of engine camera. So this concept is called as laser form. So it's a process called as die-less manufacturing. So you don't require a die. So using a laser, you can just bend your thing based on it. We have done some kind of brake pedals and clutch pedals also using this kind of way. And you have to quantify it. The important thing is you refer some. So this is a kind of laser-based shock cleaning process which you have employed in our lab. So this is a SMA-based composite flapper which is used in which can be used in missiles. So this is a kind of DRDO project which we got. We have already performed and we have transferred the results to them.
If possible.
This is what. Oh, sorry. I think there was some error was there. Okay. So this is what is called as an SMA bimorph. So the proper working principle of SMA bimorph. So this SMA bimorph, we have a capability to fabricate these SMA bimorph even on a 1 meter by 1 meter area. And so people who are interested, we can just supply this bimorph at free of cost so that we can do some certain amount of experiments. So this is a small SMA-based robotic fish which we have developed in our laboratory in collaboration with DRDO. So basically, this is a underwater robotic system which basically biomimics a jellyfish kind of arrangement. This is a fish which we have developed in our. Printed. So normally, whatever piezoelectric which you get, these are kind of. So we are working towards lead-free system for some kind of different applications such as triboelectric. So here, one of our student is making an arrangement. So when he stands on it, power gets generated, and he is using it for some kind of chemical reaction. So we also work on this is a kind of device. This is a kind of student activity. So they made a burglar alarm. So self-energized burglar alarm. When someone stands on it, automatically it creates an alarm. In fact, currently we are moving towards energy harvesting. So we are trying to fabricate these piezoelectric structures in the form of a flag. So this is a wind tunnel experiment. During a wind tunnel experiment, we are trying to see how the harvesting takes place. So this is a piezoelectric integrated structure, and through the wind tunnel, you have air which is passing through, and from that we are trying to harvest the energy. So currently we are also into this 4.0 to monitor the machine tools as well as some kind of automotive. So we have a flexible triboelectric nano generators which we have developed, which can be directly integrated with the machine tool, so that you can see how much. So whenever there is a huge amount of vibration is there, it can be easily harvested. Okay? So with this, I am closing my lecture. So if there is any questions, I would be happy to address. Okay, so I think there are some questions are there. How can we define diaphragm? Okay, diaphragm in MEMS. So diaphragm is a kind of a thin, what I would say, an elastic medium. So this diaphragm, the main point of this diaphragm is, so when you try to actuate it, it can actuate at a high frequency. Okay, so it's a thin, flexible membrane. We normally call it as diaphragm. Okay. In fact, these shape memory alloys can also be employed as similar to a diaphragm. Can we get access to this instrument? Yes, of course. So these are government funded instruments. So anytime you are free to access. What do you mean by Industry 4.0? See, Industry 4.0 means like when we talk about industry revolution. Okay. So in fact, in my first slide, I have discussed about the different industry revolution and how it is mapped with the mechatronics. So Industry 4.0 is the fourth revolution where you have internet as your main abundant source, and from that you are trying to make your system smart, okay, which caters your current demand, okay, so that you are just giving more flexibility to the system. So by giving more flexibility to the system, you get a wider window of profit. So that is one major advantage of this Industry 4.0. Any other questions? So
Yeah.
okay,
So
I will be just sharing my email ID. So in case if there is any questions or doubt, you can just post it to my email ID. So I'll be happy to address it. Thank you.
thank you. So it is a very good and innovative lecture, sir, and we have covered what is mechatronics and what is MEMS basics, starting from introduction, and we have shown what are the different research areas where you can able to do in micrograph that is actuators, and now this is opto mechatronics is also another good area where you can able to do a lot of research on that. So I think it is going to be a nice interactive lecture, and the participants have learned some nice knowledge or some new things they have taken home to them. Okay, sir. Thank you very much, sir, for your patience from morning to evening. So for
Thank you
your
very much.
sir, thank you very much, sir. Okay.
Thank you.
Thank you.
Thank you.
Thank you, sir. Thank you very much, sir.
Thank you. Bye.
Yeah, the participants, thank you for your patience, sir. Just I will start, or shall I want to take one small 5 minutes break? I will start. Right.
Sir, this is Upendra. Actually, we need to make that announcement. I shared the feedback form.
Yeah,
So
yeah.
shared on the in the chat box as well as simultaneously on the WhatsApp group also.
So please fill that feedback form. So that is going to be your attendance will be considered that depending upon that only. So yeah. So then just I will I will start it, and we will quickly wind it off the last session of today. So today just I want to discuss you about we have planned this particular session in such a manner that you can able to have live basic information about what is mechatronics, and also you can able to have some exposure on what are the different research areas which are going to be there. At the same time, you can also have some light on what are the different MEMS introduction, and what are the different research areas what we're going to be having. Okay, so at the same time in the as the day by day increasing, we are going to be going more deeper into the concepts, and we are going to give more insights in how this particular mechatronics and MEMS has been going to be used in Industry 4.0, and how you can what are the latest researches which are going to be there that we can able to see in the coming things what going to have. Okay, so as we have already seen today, just I will share my screen and I will give you now today we will start with the introduction that is modeling and so modeling simulation of mechatronic systems we will able to discuss. Is my screen visible?
Yes, sir. It's
Upendra?
visible. Yeah,
Yeah.
it's visible, sir.
So okay. So then today just I want to discuss about how you can able to model a mechatronic system. So basically, we are going to have two different important techniques we're going to be there. How you can able to do that? That is one important technique is by using the block diagram technique, and another is the bond graph technique. Is going to be the two important techniques how you can able to make any particular interdisciplinary components what we're going to have. So simply, if you're going to have a synchronous integration of, so since we are going to be considering this mechatronics is not a single domain system, it is going to be contain both mechanical, electronics, and computer components will be there. If you want to make a model for this particular system, we need this separate technique called is going to be called as the bond graph technique, or the graph bond graph technique, or block diagram technique is going to be one of the two important things which are going to be required. Okay, so coming to this particular definition, the mechatronics, it is, as I explained, it is going to be described as interdisciplinary design methodology which solves primarily mechanical oriented product functions through the systematic manner. So it is going to be an integration of both mechanical engineering, electronic controls, and systems, which is going to be there. That I will able to show you in this particular thing. We are going to have from the mechanical components and electrical and informatics what we're going to have. So this is the three things which are going to be important in this particular mechatronics point of view. Okay, so coming to this particular sensors and activators, which are going to be mainly comes under the mechanical point of view, and the signal conditioning which is going to be comes in the electronics point of view, and the digital real-time control is going to be comes under the informatics what we're going to have. Okay, so if you will start with any particular mechanical engineering system, you will able to get some mechanization. So it will be a 4-bar linkage or anything mechanization. If you add this particular electrical technology to this particular system, we are going to be getting electromechanical systems. If you add this particular electronics and informatics systems, then you're going to be getting the total the mechatronic system is going to be coming what we're going to have. That is how you can able to develop the total mechatronic systems which are going to be there. So we are going to have two different important types of the mechatronic systems is there. So one is for product oriented. Okay, so one is we are going to be having a product oriented. We are going to have we have to develop one exact product. We have to develop that one. So as morning sir has explained, we are going to be having some washing machine. If you want to develop how you can able to make that pump, that is going to be a product main based approach is going to be there. Another important thing is you can able to have you can have a function based structure also. You can able to have, you can able to have one function based structure also will be there, which we can able to make some environmental on that particular environment, how these particular functions are going to be there. So this the one best example is your automation. So when you're going to be doing in your automation, if you're going to do in that the robots we're going to be having, which is going to be working in that particular automation area. So in that particular robots, we are going to be giving some commands will be given, and that particular commands are going to be executed on that particular environment where it is going to be working, and from that particular environment we are going to be getting the feedback, and accordingly we can able to give that one. So it is going to be called as a function based structure what we have. So these are the two important things where the mechatronics is going to be mainly used case. So when you're going to be considering the history of the mechatronic systems, we are going to be having broadly three classifications are that is we are going to have the class 1, class 2, class 3, and class 4 are the four classifications what we're going to be having. The mechatronic systems are going to be divided. So primarily the mechanical products with the electronics incorporated to enhance the functionality. So if you want to enhance the functionality, then you have to use this particular thing. And in this example is the CNC machine tools that is going to be mainly used as the class 1. And in the class 2, we are having the traditional mechanical systems with significant updated internal devices incorporating electronics that is there. So it is going to be mainly containing the automated manufacturing systems, or we are going to have the autonomous or the automated manufacturing units, like automated cement factories, or whatever the companies, that is pharmacy industries, like that will come into that one. Okay. So next we are going to have retaining the functionality and the traditional mechanical system, but we are going to have, we will able to replace the total with electronics. So here the one example is your digital watch. So the working of your digital watch, previously we are going to be using the mechanical components by using the gears and springs we are going to have. Now that that has been replaced by your digital systems, but the watch is going to be working as the same thing. So like we are having a needles, and the small needle and the big needle will be there, the same thing which are going to be working like that one. Okay. So next we are going to have the fourth category, that is the present trend, that is intelligent systems which are going to be using the different synchronizer technologies what going to have. Okay. So this is a small cartoon why we need for the mechatronic systems what we're going to have. So we are going to be using why we need this particular mechatronic systems, and in your daily life, if you see here, if you see your daily life, all the systems are going to be in your daily life, whatever systems you are going to be having, all are the mechatronic systems what we're going to have. Okay. So if you see here, the main task is going to be, if you want to kill a rat like that, if you're going to give in for different domain of engineers which are going to be there, the different people will have the different technology what we're going to have. Okay. So this particular mechatronics means it is going to be an integration technology of all the different domains to get the same particular task to be done in a more appropriate manner. That is going to be the concept why we are going to for the mechatronics which are going to be there. Okay. So next. Okay. So now if you see here in the modern mechatronic systems, now we are going to be having this particular industry 4.03 concept, 4.0 concepts are coming, and we are going to be having this IoT concept also coming into that one. Okay. So now these IoT things are also incorporated into this particular mechatronic systems, and how we can able to develop new integrated that will comes considered as the mechatronic systems which is there. Okay. So just in a glance, I will show you how you can able to, if you want to model any particular mechatronic system, it will be divided into the subsystems like that. Okay. So we will have a base system will be there, a base module will be there. So this particular base module will able to contain some information system will be there, and some sensors and actuators will be there. And these type of base systems are going to be connected in different modules, and these modules we are going to be connected to different connected systems what we're going to have. Okay. So that is how the total the mechatronic system will be able to contain. Is going to be the big system will be there, and we are having different the subsystems will be there. So each subsystem is going to be having some different modules will be there, and these sub modules will able to have some base systems will be there. Okay. So this is going to be one main system, and from this we are going to have sub modules will be there, and this particular sub module you are going to be having the main system what we're going to have. Okay. So this is one example how we can able to develop one mechatronic system for a crossroad control. So we are going to be having a crossroads are there. Now with this technology is going to be called as a V2V vehicle, V2V technology, that is vehicle to vehicle technology. So this vehicle, and this is going to be one vehicle, and this is going to be another vehicle. These two vehicles will able to communicate with each other while they are going to be having the cross of roads what going to have. Okay. So in that case, if you want to develop or design any particular system for this type of thing, then we are going to have this is going to be the main system, and the subsystem or modules will be considered as the car, and the different subsystems what we're going to be having is the different control the base systems, like what are the different sensors, and what are the different actuators which are going to be used that one. Okay. So that is how you can able to design the mechatronic system from this one. Okay. So the main concept of this modeling and simulation will able to comes under the picture is how you can able to design a particular mechatronic system starting from the base systems. Okay, so here this is going to be the one small abstract which we are going to be coming. So if you see here, we will able to see, we'll start with the mechatronic system, device systems we are going to be there. And we are having, we can able to get the cyber physical systems are going to be coming. And once we are going to be getting the Internet of Things what going to help. So we have to start from this, the mechatronic systems, and we can able to go for the cyber physical systems and Internet of Things what going to help. That is how we can able to help. Okay, so this is going to be the integration. The mechatronics will be considered as the integration of all these particular subsystems what we're going to have. So just I will skip this one. So these are going to be the different technologies we are going to be required to get the advances of this particular mechatronic systems is starting from the mechatronic system, and how we can able to develop a cyber physical system, and how we can able to make a cloud-based IoT system. That is going to be the different technologies which are going to be required for this one. Okay, so we have to start with this particular mechatronic system, then we have to go for the cyber physical system. You have to design that one. Once you got this, then you have to go for the cloud-based IoT system by incorporating that one. That is how you have to design the system for this case. Okay, so these are the basic key elements which we are going to be using in the mechatronic system. So we are having the mechatronics is going to be considered as simulation and modeling and automatic control and optimization plus mechatronic systems and electrical systems and computer systems. And this is going to be explained by Palani sir. I did not want to go in deeper into this one. I will skip this one. Okay, so this is the block diagram. The what we're going to be having. We are going to be having the signal conditioning will be there, and the sensors will able to give the signal conditioning, and analog to digital controllers will be there. And from this particular controller, we can able to get the digital to analog, and we can have the actuator driving system will be there. Okay, so if you consider the another important scenario in this particular mechatronics is the fault detection. The fault detection is going to be another important thing which we are going to be seen in the mechatronic system. So how we can able to do is first we have to make the process model has to be done, and from this particular thing we have to make the feature generation is going to be done, and from this we can able to detect the what is the change in that particular feature can be detected, and the particular false diagnosis is going to be done. Okay, so why we have to do this fault diagnosis is depending upon the fault tolerances, we can able to have three important types of systems will be there. One is the static redundancy, another is the multiple redundancy, and the third one is the cold stand redundancy is going to be another important thing what going to help. So in this particular first one, we will able to have, if any particular one system is going to be got faulted, then another system is going to be getting activated into this one. Okay, so this is going to be called as one of the redundant systems what we're going to have, where we can able to use n number of systems are going to be used in that one. Okay, so whereas in this particular standby module systems, we are going to be having two systems will be used there. One system is, second system is also continuously running whenever the fault is going to be occurring in this particular system one, we are going to be getting the system two is also get connected into one. Okay, whereas in this particular third category of the fault detection systems, what we're going to be having is you have one the second the standby system is going to be kept here in this particular manner, where this is going to be gets into activate when the fault is detected, and the first system has been failed, then the second system is going to be activated. In this case, both the first and second system both will be acting continuously, whereas in this particular thing, the second system will able to comes into activate when the total the first system has been failed. That is going to be called as the cold standby. It is this is going to be called as the hot standby what going to happen. So that is how these are the two important standby systems what we're going to be having. So for this, if you want to make the fault detection for this particular thing, you have to make the modeling has to be done that one. Okay, so just I will skip all these things. We are going to have the fault detections where we are going to be using is this in the automobile area as where these mechatronic systems are, as this is going to be main application is in the automobile area. Presently, a lot of research is going on that, and autonomous vehicles are going to be designed there. So this is going to be one of the Tesla car where you can able to see you can able to see the self-driving car of the Tesla. This is one small video you can able to see.
Start this video. I want to clear something up and address this.
So this is how you can able to make the self-driving car is going to be one of the important case. Okay, so if you want to make this type of modeling has to be done, then we are going to be have two important things will be there. One is the process model, the process will be there, and the simulation tool will be there. Here, this is going to be called as a simulation tool, and ECM model will be there. This is going to be the electronic control unit will be there, and the real process will be the engine what we're going to be using that one. Okay, so if you want to have the software system is going to be connected to this particular the real system, then it is going to be called hardware in loop simulation, what we're going to be called. Okay, so similarly, if you're going to be having the process thing and the simulation tool and the controller is going to be interacting that one. Okay, so this is going to be called as a software in loop simulation, what we're going to be considered. Okay, and if this particular controller and the real engine is going to be communicating, then that is going to be called as the rapid control prototyping is going to be called. Okay, so these are the three important simulations what we can able to do in the mechatronic system before making the detection of the system what we're going to have. Okay, just 1 minute. Hello. Is my voice is audible? Hello, Upendra?
Yes, sir, it's audible.
Okay, it is clear only, no? Somebody
Yes, sir. It's clear.
Clear, okay. Okay. So then we will able to go further. So then we will able to see one small example. Just I want to show you here. This example will able to how we can able to have the braking system in a particular automobile system. We can able to have. So here this is going to be the automobile braking system. So this automobile braking system, if you are going to be having how the braking system is going to be there. So we have to design the braking system, the fault tolerance what we have. So if the brake has been failed, it has to stop the particular vehicle. How that is going to be called as a fault tolerance what we have. Similarly, for the steering systems also, we are going to have different types of steering systems which are going to be there. The hydraulic power steering system and electrical power steering system, and electrical power assisted steering system, and active front steering system, and steer by wire is the three important steering systems what we're going to be having, and these systems are going to be mainly used for the standby systems what we're going to have. Okay, so if you coming to this particular modeling, the system, as I explained you, we're going to have the system will be there, and this particular system is going to be consist of different subsystems. As the mechatronic system is going to be there, you have to model the system. Suppose you are going to consider this is the washing machine. What we're going to be considered, this washing machine is going to be have the different components are there. So here I am showing this the controller, electrical and hydraulic system, and mechanical and thermal systems are there. Okay, so these the colors what are we going to have. Each system is going to be having these type of the color indicates the indication of the type of domain area which is going to be present in this particular washing machine what we want to have. Okay. Similarly, for the hydroelectric steering system, if you want to have this particular steering system, here also we are going to be having the different domains of knowledge integration is going to be required if you want to make the model for that one. Okay. Similarly, for the IC engine control. Okay. Similarly, here also you can able to have the different domain knowledge integration is going to be required for that one. Okay. So now we are having the hybrid vehicles are going to be used here. These hybrid vehicles also will have the different integration of the controllers, electric and hydraulic and pneumatic systems is going to be there. Okay. So here, if you want to make the model for this particular thing, so then each domain has to be considered, and you have to make the modeling has to be done. Okay, that is called as the multi-physics model or the dynamic system modeling is going to be considered in this case. Okay, so we will be able to start with the equations, and we can able to have the physical iconic representation is going to be there, and this is going to be the two different types of things. So if you are writing this particular using this particular equations, then it's going to be called as the mathematical model. Okay, and this is going to be considered as the physical representation model what we going to have. Okay, so the physical representation or iconic model will be mainly considered when in this case the length of the components also will be coming into there, whereas in this particular mathematical model you cannot able to incorporate the different length components cannot be incorporated into this one. Okay, so in this case the technique what we're going to be using is the block diagram technique is mainly used for this one. Okay, so next important thing is if you want to consider the power flow and the power consumption. Okay, how the power is going to be transmitted from the electrical systems to hydraulic systems, and from this particular hydraulic systems to the mechanical systems, then it is going to be considered. Then we have to consider the Bondgraph technique, which is going to be mainly used for the power flow technique, which are going to be used there. So from this you can able to how the flow is going to be considered, that technique is going to be used that one. Okay, so in the design of this particular mechatronics technique systems, we will able to consider mainly the V model has been considered. Okay, the V model will able to mainly contains the representation of the system integration, and the system engineering domain will be there, and the component engineering domain will be there. So this is going to be the component engineering domain where the individual components has going to be designed here. Okay, whereas in this particular system engineering domain, these ones this is going to be coming in this particular down manner, and once we are going to be getting the components has been done, it is going to be coming for the implementation manner what we're going to have, and in this case we are going to be having some verifications are going to be done in this particular manner what we're going to have. Okay, so this is one example where you can able to see how in a Ford product car manufacturing, how you can able to start from the customer requirements or the vehicle inputs what are going to be required for this one, and from this the vehicle level requirements has going to be considered, and after that the subsystem level is going to be considered, and finally we can able to have the integrated parts will be considered that one, and then we'll have the system verification and vehicle verification, and disposal will be there, and each area they will able to have some validation is going to be done. So this is going to be called as the V type approach of designing of mechatronic system is going to be mainly considered. Okay, so if you see here the mechatronic system overall block diagram, we'll have the mechanical skeleton, electronics, and the control is going to be there. So the mainly the mechanical things which are going to be consists of the activators, and the mechanical systems like your robots and physical and automobile is going to be considered here. And in the electronics point of view, how you can able to have the sensors, signal processing, and power interfacing is going to be done. And in the controls, we're going to be having the PLC controls and the embedded systems what's going to be there. Okay, so with this, just I will show you. This is going to be the mechatronics design process where we will start with modeling and simulation. That is the need of recognition of need, conceptual design. We will start with we will able to have a mathematical model will be there, and then sensor and electro actuator selection, and detailed modular mathematical model will be there, and then control system design will be there, and design optimization is going to be done there. Okay, so once this has been done, if any particular changes is going to be required, once again it will go to the first conceptual design technique, and then we are going for the hard in-loop simulation. What going to have? I already explained you what is the hard in-loop simulation, where this particular software simulation can be incorporated with the in real-time sensors and actuators which are going to be there. Okay, so once they have been designed, the design optimization is going to be done, then it will be able to go for the deployment of the embedded software what's going to have. That is how the total design process is going to be done in the mechatronic system what going to have. Okay, so this is the same thing what I have explained you previously, the web-based case what we're going to have. So this is one small example for the control system design. So this will be covered tomorrow by one of the IIT professor. He will able to explain an overview of the control system, how you can able to do that. Same, but example I have given you. We have a theoretical model is there. Then we are going to be getting a simulation model. And from that, we are going to be getting the controlled prototype. We are going to be coming, and then we will able to make one hardware in loop control, and then we will able to validate, and finally we will go for the application for the particular cost system what we have. So we are going to have two different types of simulations is going to be there. Why we need this particular modeling simulation is we are having the real model, real world is going to be there. How you can able to represent this particular real world in a understandable manner to the computer what we have. That is mainly we can able to do the physical or ionic models, analog models, and mathematical and symbolic models what we have. So mainly we are going to be concentrating on how we can able to make the mathematical models for this case. Okay, so this we are having for any different systems are there. So the static systems, dynamic systems, as you know that the static systems are no change in time. It is called the static systems, and the dynamic systems, the system changes with time. It is called a dynamic system, and we are having mainly the real systems which are going to be present are all of dynamic in nature because they are all will change with respect to time. We are mainly concentrating on this particular the system development. So if we are having a system is there, we can able to make experimental with the actual system, and experimental with modeling of system. This will able to do the physical modeling and mathematical modeling. In the mathematical modeling, you can able to go for the analytical solution or simulation. In the simulation, you can able to have frequency domain analysis or time domain analysis and hybrid domain analysis. You can able to do that one. Okay, so the same thing here. This is going to be one important slide I can tell you. So we are having a topological model, physical model, mathematical model, and numerical model. These are the three important things what we're going to be have. So in the topological model, we can able to get the exact dimensions of the component also you can able to incorporate. So what is the diameter of this particular shaft? What is this is the length of this particular shaft that we can able to incorporate in the topological model, whereas this can be represented in the physical model in the form of the spring damper systems what we're going to have, and in the mathematical model we're going to be getting the equations form. Okay, so in the physical model and in the mathematical model we cannot able to have the exact dimensions will not be there. So that is one drawback what we're going to have. So we have to go for the topological model, and in the numerical model it is going to be coming in the form of graphical representation where we can able to analyze the stability of system. Okay, so coming to this particular mathematical modeling, we are having the different categories are there: static and dynamic, linear and non-linear, time invariant and time variant, single input, single output, multiple input, multiple output, continuous and discrete, and deterministic and stochastic is going to be another important different categories what we're going to be having. Okay, so So time invariant and time variant also I explained you. So the linear time invariant models are mainly considered for our control systems. What we are going to be considered fun. Okay, so because they are going to be, because they are the mathematical structure will be simple. Want to go for LTI models, the mathematical model will be of simple stage. We can able to make them in a somewhat easiest manner. What one. So similarly, we are having the single input and single output and multiple input and multiple output techniques are there. So where we are having a single input and single output is there, then transfer function technique is going to be mainly used there. Okay, whereas if you are having the multiple input and multiple output technique is there, then we have to go for the state space equations are mainly used for deriving in this particular case. Okay, so if you see here the transfer function technique, which we can able to use, which will have one particular proper input will be there and proper output will be there, and we can able to get the relationship between this particular proper input and output by using a transfer function, and this we can able to analyze that one. Okay, whereas if you're having a multiple inputs and multiple outputs is there, then you have to go for the state space model. We can able to use that one. Okay, so coming to this particular continuous model, as the continuous time has dependent variable, therefore input output take all the possible values in a range, and the discrete model has a discrete time as a dependent variable, and therefore input and output takes on values of specific time only in the particular range. Okay, so if you are having a continuous model, we have to use the differential equations, integration, and Laplace transfers are mainly used that one. Whereas discrete models, you have to go for the difference equations and summation and jet transfer things which are going to be mainly. Okay, so first we will able to see the block diagram representation. Okay, so how we can able to use the block diagram representation for any particular system are suitable for representation. We can able to see the particular block diagram. We'll have one summing junction is going to be there. We'll be having one summing junction will be there, and one gain will be there, and one integral will be there. Okay, and one feedback will be there from this one. This is going to be a representation of the basic components of any particular the block diagram system. Okay, so if you want to represent any particular real system in this particular form of the block diagram, then we can have the block diagram. We are having the different reduction techniques is going to be used if the systems are going to be connected in series or connected in parallel, or we are having a feedback system, a negative feedback or a positive feedback. Depending upon that, we are going to be having some reduction techniques is going to be used, and the takeoff point reduction technique, and these are all some of the reduction techniques which are going to be used for simplification of this particular block diagram. Okay, so once you will simplify it, you will able to get a particular relationship between the input and output in this particular form. This is going to be the standard block diagram representation, how you can able to do that. Okay, so if you have the mechanical systems, if you see that one, we are having different the translation, linear motion or rotary motion is going to be the two important mechanical systems are going to be there. If you consider the linear systems, we are going to have the spring, okay, and damper and mass is going to be some of the three important components which are going to be used at that point. Okay, and by using this particular thing, if you develop the mathematical equation, that is going to be considered as the spring damper system, which is going to be considered as MA is equal to F minus K X into C this one. So if you want to represent this in a block diagram representation, so these are some of the important steps which are going to be followed depending upon that one. So we will able to start with the D, the differentiator, and 1 by D is the integrator. So what we will do is we will able to take 1 by D and this one, and you have to take the x dot here. If you want to integrate this one, you are going to be getting x dot, and finally you are going to be getting x. Okay, and whatever the equation which are going to be representing here, this I can able to represent in this particular block diagram representation by considering this one. Okay, so here x double dot t is multiplied by minus b by m. Okay, so here this one is 1 by m and this is going to be b. Okay, so this is how we can able to represent and finally if you want to reduction this one we are going to getting this is going to be how the block representation of this particular equation is going to be represented. Okay, so similarly if you take a two spring mass system, so that then you're going to be getting these are two different equations. So if you consider the free body diagram for M1 and what are the equation you're going to get, this is the differential equation. If you consider the free body diagram of M2, we are going to be getting this is the differential equation you're going to be getting. And if you combine these two differential equations, we will able to get this is going to be the block representation of the total system what we're going to be getting. Okay, so that is how you can able to represent the two mass mechanical systems what we're going to have. The main example for this particular thing is in your railway systems when you are going to be having this particular system is going to be connected to this particular thing. Okay, so this is going to be mass 1 and this is going to be mass 2. So these are two are going to be connected to each other, and if you want to model this type of two carriage train system, then you have to go for this type of case. Okay, that is how the transfer function is going to be developed taken, and from this particular transfer function you can able to analyze by giving the different signals as one input signal as step input, or you can able to analyze that particular thing. So one proper session is going to be given on this particular MATLAB session. Tomorrow afternoon we are going to be having the MATwork people are going to be coming. They will able to give you in detailed about how you can able to model this particular mechatronic systems in the MATLAB starting from the starting from the base model systems what we have. That is now I am showing you how you can able to analyze the particular systems, but you can able to make physically analyze that particular systems there. Okay, similarly if you want to have the rotational systems are there, one basic example is the flight control systems where we will able to have the two rotation mass will be there. Okay, so the rotational mechanical systems also will have in place of force we are going to be getting the torque. Okay, in place of velocity you are going to be getting the angular velocity. In place of acceleration you are going to be getting angular acceleration, and in place of mass we are going to be getting moment of inertia. This is going to be the difference what we're going to have, and we are going to be getting the differential equation in this particular form. Okay, so similarly we can able to have rotational translation systems also, like your rack and pinion systems, where we'll have both rotation and translation will be there. Okay, and that differential equation you can able to generate by using this particular formula what we're going to have. Okay, so these are some of the important things which you have to remember in the translation rotation systems. The J value, as we have already explained you, this moment of inertia is going to be calculated in the if you are considering a lead screw, this is going to be the formula will be considered. If it is the rack and pinion, the J value is going to be considered. This is going to be used the formula. And if you want to have a conveyor belt system, then you have to use this is going to be the formula for the J value calculations what going to have. Okay. Similarly, the next is important thing is the gear trains. So these gear trains are going to be mainly used in your mechanical component. This is also another important mechanical component for transmission of power. Then how we can able to get the differential equations is by considering the torque ratios to the theta ratios. We can able the angular velocity ratios. We can able to get this one, and we can able to design this one. Okay, so just I am skipping all these things for your. Similarly, for the electrical systems, we'll have the capacitance, resistance, and inductance are the three important components which are going to be there in the electrical systems. And by combination of all these three basic components, you can able to get the combined system. We can able to get it. Okay, so these are all how you can able to make the block diagram representation. That is how you can able to represent the block diagram, and you can able to analyze this in the MATLAB simulating systems. Similarly, the fluid systems also you can able to have. Just I will skip these things. So we can able to model these cases also. So one important thing you have to remember is we'll have the analogies also will be there. Okay. So why we use this particular analogies is you can able to represent the domain. So one mechanical system I can able to represent in the electrical form, or then hydraulic system also I can able to represent in the electrical form. Okay. So these are the two important analogies we can able to use in this particular case for simplification. So if you want to have the force voltage analogy is mainly used in the Bondgraphs, whereas the force current analogies are mainly used in the mathematical scenario or your block diagram representation what going to have. Okay, so this is one small example where you can able to see this particular case of the suspension system, the car suspension system. We can consider this is the car suspension system. This is the tire, and we are having the wheel, the base, and then we are having the suspension system and the passenger mass what going to have. Okay, so this is going to be the off suspension system. If you want to design this particular suspension system, we can able to represent this in the mathematical form, and we can able to get this particular equations, and by solving this we can able to get the case. Okay, so just this is one small case where one of my PhD student has done the highly redundant activators, how you can able to design highly redundant activators which are going to be there, which is mainly used for the flight failure. So if you want to have any particular flight is going to be occurring, we are having the actuators are mainly used. So where these actuators are mainly used, here just I will show you one the flight control, then I will go and I will get back. So here if you see this particular flight control, so if this flight has to be controlled, then we are going to be having some different activators are going to be used that one. Okay, so these activators are mainly used for different for different movement of the wings, everything. So if you want to get the roll control, these are the different activators. The wheels has to be moved. Okay, so by rotating this particular thing, they can able to give you the action of this particular flight has to be given. Okay, so this you can able to see this in a more understanding manner. If you see this particular video, if you want to have the flight control has to be done, these are the different controls has to be used. So this is how if you want to have a rolling action is going to be required to make this. Similarly, if I want to have the tail also will able to have different control will be there. Okay. So the flight will have these two controls depending upon the trail and the wing control. The flight can able to get the roll and pitch action will be there. Okay. So if you want to get this particular roll and pitch action, we need some different activators is going to be required. Okay, so that activator which is going to be considered as this is going to be the activator which we are going to be using. Okay, so this is going to be the activator. Okay, so if this particular activator will able to act, so to get this particular the action of this particular the tail or anything. Okay, so this tail action is going to be considered as the ailerons, where this particular ailerons is going to be moved up and down by this particular activator. Okay, if this particular activator will fail to get this particular motion, then the fire clash is going to be occurring. Okay, so to overcome this particular thing, what we will do is we will able to design one particular a highly redundant activator is going to be there. Okay, if one of the activators fails also, we can able to get the same motion has to be get to this particular thing, so that we cannot able to get the flight accident cannot be occur. So how you can able to do that? This is going to be we will able to consider starting from an electromechanical activator, and we will able to make the different highly redundant activators by having the different combinations what going to have. So we can able to make three or four activators will be connected the same manner. If this activator fails also, these two activators will able to get the same position. That is going to be called as the highly redundant activators what going to have. Okay, if you want to design these type of systems, then we will able to have, as I explained to you, we will able to have start with the basic subsystem. This is going to be the basic subsystem what we're going to have. This is going to be the basic activator, and these type of basic activators which are going to be present in different combinations of series and parallel combinations will be there. Okay, so by connecting this particular modeling this one, we have modeled this particular thing in the MATLAB Simulink only, and this is going to be how the single activator is going to be working, how the single activator is going to be working. Okay, so if I want to, if this particular single activator, if you are going to be using for that particular aileron principle, if this particular activator will fail, the total aircraft air is going to be crash will be able to occur what won't help. Okay, so to overcome that one, what we will do is we will able to make a combination of different activators. So this is going to be the combination of different activators. Okay, so this is the module activator is going to be considered. So single, we have considered this is going to be a single system, the base system. As I explained you previously, we are going to be considering this is the base system. By combining these particular base systems, we have made a modular activator or the redundant activator is going to be made like this. Okay, and this is going to be the block diagram representation of the 3x3 HAR. The 3x3 means we are going to be having 3 activators in the series combination and 3 activators in parallel combination are being connected, and that will be connected to this one. Okay, so if you make this particular 3x3 activator, it's going to be looking like this. Okay, if you want to model this 3x3 activators and how these particular 3x3 activators are going to be working, then you have to make use of the Simulink, the MATLAB Simulink is going to be mainly used. Okay, so if in this case you can able to give different faults here. If this particular activator has been failed, or this particular activator has been failed, then how this particular movement has to be achieved. That is going to be called as the highly redundant activator you can able to design. This is going to be one of the small project which has been done. Our student has been done. And this is how the redundant activators is going to be working that one. Okay, so this is how the actual redundant activators will looks like, and these type of redundant activators are going to be kept in different positions of this particular air flight. Okay, these are going to be the different air flight which are going to be flights what we're going to have. So if any, so that we can able to get the flight moment can be destroyed what would have. Okay, so this is how you can able to make the model. You can able to make the model and you can able to. So you can able to make the model and you can able to simulate it. So just this is how we can able to do it. So if you have any questions in this, you can able to ask me up to now. So this is how you can able to make the block diagram representation of any particular system can be made in the block diagram representation. You can able to do that, and similarly you can able to simulate the systems. If you have any doubts up to now, if it is okay, means we can see how you can able to model by using the Bondgraph technique also. I will able to explain that one. Okay, is it clear, participants? If you have any doubts, you can type in the chat box. Yeah. I think this is going to be today is going to be, so we will have the hectic weeks only every day. So the last lecture will be somewhat difficult for you to digest, but these concepts are somewhat easy only. That's why I'm skipping it a little bit fast. Okay, is it clear? So then we will able to see the further modeling. I will start sharing. So next important technique how we can able to model any particular mechatronic system is going to be by using the Bondgraph model. Okay, so this is going to be another important technique how you can able to use the technique. So here in this particular Bondgraph technique, what is the difference between this particular thing is in the block diagram technique, we will start with the physical system. We will able to make an engineering model, and we'll able to get the differential equations, and that differential equations we'll able to represent in the block diagram, and then we'll able to make the simulation what we're going to have, and finally you're going to be getting the output. Okay, whereas in this particular bond graph technique, we will start with the physical model, engineering model. We will not have any particular differential equations. Finally, we will able to make one bond graph, and we will able to use one bond graph simulation software will be used, and we are going to be getting the output what we're going to have. Okay, so these two steps will be skipped, and these two steps are eliminated in this particular bond graph what we have. So we are not required to make any particular differential equations is not required in making this particular the bond graph model what we are going to be using. Okay, so this bond graph model has been invented mainly in it is not it is very old model. So it is an abstract representation of system. It is an abstract representation of system which collects the components interacting with each other through energy ports and place in a system where energy is exchanged. Okay, so what we're going to be doing is we will able to represent in the form of the different bonds. Okay, so these bonds will able to have two important bonds will be there. One is one is called as zero junction bond, and another one is called the one junction bond what we're going to have. Okay, so I will able to explain you what is zero junction bond and one junction bond. Before going to that, we will have this bond diagram consists of the subsystems which are either described as idealized elementary process or non-idealized process what we're going to have. Okay, so idealized elements means that is going to be the final product. Okay, suppose if you are going to be taking an electrical component, this current resistance, this is going to be the final components what going to have. Okay, so if you are having further non-idealized process means this is going to be a subsystem is going to be there. Further we will able to have some more further subsystem is going to be connected, that is going to be called as the non-idealized process what going to have. Okay, so you can able to connect the bonds between the zero junction and one junction. You can able to connect non-idealized process or an idealized elementary process also you can able to connect and you can able to make this particular bond that what we have. Okay, so in this particular thing in the subsystem bond graphs, mainly we are going to be using the power ports or the signal ports are mainly used there. Okay, how the flow of power is going to be flowing from this particular system one to the another system, that will be represented in this particular manner. Okay, so we'll have, as I know told, we are having two important junctions are there, zero junction and one junction, and this zero junction will able to have only the flow of flow will be there, whereas in one junction flow and effort will be there. Okay, so this will be the bond graph will able to have two important variables are there, effort and flow. As this is going to be multiplication of effort and flow, we'll able to consider as the power. Okay, suppose if you are going to be considering any particular system, one actuator, if you consider from this particular system, I want to move this particular actuator, it will be, I need some effort is going to be required to this particular thing. Okay, and this effort multiplied by how much force I am going to be, what is the flow? So flow of, because the effect is going to be transmitted in the form of what signal is going to be transmitted. That multiplied this two is going to be considered as the, what is the power is going to be considered in this case. Okay, how much power is going to be transmitted from this particular subsystem to this particular system, and from this particular subsystem to this particular system. That is how we will able to represent in this particular Bondgraph theory what going to happen. Okay, so this is how we will able to represent in this Bondgraph. This is mainly used, you can able to analyze mechanical systems, electrical systems, mathematical systems, or pneumatic systems also you can able to use. Okay, so he is going to be one of the easiest manner how we can able to do is the differential equations, that is the math will not be there. The Bondgraph technique, the math will be calculated by by the software itself. There is no need for you. You have to identify how the power has going to be transmitted and what is the flow is going to be there. Okay, so this will able to these are the three important flow parameters. If you consider an electrical system, the effort is the voltage and the flow is the current. If you take the translation, mechanical translation system, the force is the effort and velocity is going to be the velocity is going to be the flow. And if you take the rotational system, the torque is going to be the effort and angular velocity is going to be the flow what we're going to be having. Okay, if you consider the hydraulic system, the pressure is going to be the effort and volumetric flow is going to be the flow what going to have. If you take the chemical system, the chemical potential is going to be the effort and molar flow is going to be the flow what going to have. In the thermal system, the temperature and the enthalpy is going to be considered as the flow systems what going to have. Okay, so these are the some of the important components which are going to be present in the bond graph. You can able to represent this I will be represented, that is the inductance or mechanical mass will be represented, and C will be considered as the capacitance or mechanical compliance. This compliance also will be considered as the spring constant K. Okay, and this R will be considered represented as electrical resistance and mechanical viscous force. This is going to be considered as the damping force. Okay, this is going to be considered the damper. Okay, so that we will able to represent in this particular manner. Okay, and we will have another two important components will be there. One is the transformer, another is the gyrator will be there. Okay, so this transformer, why we will use this transformer means if I want to convert the effort will be converted into the same, the effort, this effort one here, whatever the effort is in the subsystem one will be totally transformed to the second system. Then we will able to use the transformer. Okay, we can able to use the gyrator. If we can, hello. If you use the gyrator, if I want to convert the effort of one subsystem will be converted into flow, and another, the flow of the subsystem one will be converted into effort. That is going to be considered as the gyrator what going to have. So this is going to be the reverse will be there. If we are having in the two subsystems, if the effort will be directly transferred to this particular the subsystem one, effort will be converted into subsystem two, then we'll able to use the transformer. If you have the effort from subsystem one will be transformed to the flow of the system, and we can able to have the reverse will be there. Then you have to go for the gyrator what point how, and we will able to have two important things will be there. One is the effort source and the flow source will be there. That will be represented by SC and SF is going to be one of the two important things which are going to be mainly used that one. So these are the three. These are some of the key elements which are going to be used that one. So by using these particular key elements, you can able to develop the bond graph for any particular system, and you can able to analyze the particular system by using this one. Okay, and we will able to have two junctions are there. I have already explained that one. One is the zero junction, another is the one junction what we're going to be having. Okay, so in the zero junction, the efforts are equal Whereas in the flow junction, we are going to be having the flows are in the one junction, the flows are going to be equal. Okay, that means the flow sum is going to be 0, whereas the effort sum is going to be 0 in this particular case. So if you're going to be considering the 0 here, the efforts will be equated, and the flow sum must be equal to 0. That is F1 plus F2 is equal to F3 plus F4 plus F5. This is going to be the flow sums what going to have. Whereas if you are considering the one junction, the flows will be equal and the effort sum must be equal to, that is effort 1 plus effort 1 2 plus this one is going to be equal what going to have. Okay, so this is how you can able to these are some of the important components which you are going to be using. So now you can able to make the bond graph for this particular same the single that is mass the force which is going to be acting for the spring mass system what going to have. Okay, this is going to the same spring mass system. We have developed one the block diagram we have developed by using this particular differential equation. Same we can able to use the bond graph technique we can able to use, and we can able to develop that one. Okay, similarly here we can able to have the effort source is here the force. Okay, the effort source is going to be here the source. Okay, and that has been transferred to this particular mass. Okay, and that has been transferred to this. We are going to be having this is going to be the end of this flow. So we are having this is going to be the effort. So Fe, we can able to have the signal is going to be flowing, and this is going to be one will be always one junction will be considered wherever one subsystem 1 and subsystem 2. So if you are going to be having two subsystems, always one junction should be used. And if you are having any internal in between these two things, two subsystems, if any connections are there, then that will be represented by zero junction, which will be represented one. Okay, so here I want to represent the subsystem. Here we are having only one system is there. I can represent this is going to be one subsystem, and this is going to be another one subsystem. So we are having junction 1 will be here, and here another junction 1 will be here. Okay, and here in this particular case we are going to be having the two components are going to be connected here. I need one zero junction is going to be required here. One zero junction has to be required. Okay, so that is how we will able to have. So one junction is here and one zero junction is here, and another one junction is going to be considered here. Okay, so one junction is here, one zero junction is there, and one more one junction is going to be used here. Okay, so now in this particular zero junction, one spring has been connected and one damper is going to be connected here. And in this particular one junction, one effort source force is going to be the effort source is going to be connected, and this particular one junction we are having the velocity component is going to be the flow. The flow is the velocity that is going to be connected here. Okay, so since it is going to be a fixed one, so since it is going to be a fixed one, it cannot able to have this the flow of this particular thing. FF is the flow is going to be equal to 0 because it is a fixed one. Okay, so this term will able to becomes 0. So this term will able to becomes 0. Okay, so whatever the terms which are going to be coming here, that will be get nullified. So then if you consider this is going to be 0, and this term whatever this all will this will be transferred to this. Okay, whatever the there is no need for this one. Okay, automatically this is not this force is this component is not there, and here also nothing is there. So directly you can able to connect these two things will be connected to here. Okay, and that simplified the bond graph will able to looks like this. This is going to be a simplified bond graph for this particular spring mass system what going to have. Okay, so once you represent this particular simplified bond graph system, automatically you can able to analyze and you can able to make the analysis of this particular system. You can able to do that one. Okay, similarly how you can able to do same. So similarly this is going to be another example for two mass systems. So here we need how many ones are there? So here it is one is going to one junction is going to be required, and here for mass 1 we need another one junction, and here also one more junction is going to be required for this one. Okay, so what are the different forces which are going to be applied? So here this is one force, and at the same time it is going to be a constrained one. This SF is equal to 0. Okay, this is f of x is equal to 0, and here one more it is there, mass is going to be represented, that I have represented as m. Okay, and here another mass is there that is represented as m. Okay, so now here one more effort is going to be the force which is going to be applied in this particular one. Okay, so now we will able to incorporate the zeros here. So what are the zeros? I can able to incorporate the zero junctions are going to be incorporated in this case. I can able to incorporate the zero junctions here, and these zero junctions will able to contain one is the spring and another is the damper is going to be connected to this. Okay, similarly here in this particular also we have one more zero will be connecting only 1k is going to be connected here. I can able to connect only 1k single k. Okay, and if you simplify this particular total system, and if you see here, since this f of s, this is going to be 0, this total thing can be eliminated. So this total, there is no effect is not will not be there. There is no flow will not be there. Okay, so once if you simplify this one, you can able to get the bond graph, the modified bond graph is going to be coming like this. Okay, so if you get this particular bond graph, automatically you can able to analyze this particular case. Similarly, for the electrical systems, we will have zeros only. Okay, we will have a zero will be there, here another zero, here another zero, and here another zero, and here another zeros will be there. Okay, so since we are not having the effort will not be there, we cannot. We will have only zero junctions. We will not have any one junction at the center is going to be only one junction at the center will be there. That is one junction will be there at the center. Okay, so now we will able to connect what are the different efforts which are going to be there, that we will able to connect here, and we will able to simplify this. We will able to get the circuit for this particular total circuit. We can able to get this one. Okay, so that is how you can able to draw the bond graph for any particular mechanical electrical system or any particular combination system. If you know what is an effort and what is the flow and what are the different junctions which are going to be occurring, and what are the compliances which are going to be there, you can automatically simply draw this particular bond graph, and you can able to simulate the mechanical systems what going to happen. Okay, so this is going to be another technique how you can able to make the modeling of the mechatronic systems by using one is the block diagram technique, that is going to be the technique which are going to be used previously I have explained, and another technique is going to be called as a bond graph technique, which we can able to use for modeling of these particular cases. Okay, so this is some of the examples where we can able to make the modeling of underwater robotic system. We can able to make the bond graph will be represented in this particular manner. You can able to make this particular bond graph, and similarly, if we are having this is going to be the 3-link robot arm. So this is going to be a 3-link robot arm. This is going to be link 1. So this is link 1, link 2, and link 3. So this particular 3-link robot, if I want to represent in a particular bond graph, this is going to be how I can able to represent that one. Okay, so if you represent this particular bond graph, you can able to make the modeling analysis also can be done what when you have. Okay, so it will be little bit difficult for you to understand starting, but once you understand this particular thing, it will be very easy for you to draw this particular bond graph, and you can able to analyze this particular system in a very easiest manner. Okay, so now these are the two important things what I want to explain you how we can able to make the modeling of the mechatronic systems, how you can able to do that one. Okay, so these are all the students which just I want to thank these particular students. These are all the PhD students who are working under me. Okay, and this is the person who has developed that particular high redundant activator case what going to have. Okay, and these are all some things, and now if you have any doubts, you can tell me. I can you can able to ask me. I can clarify it. Any doubts for you? Hello.
Participants, if you have any doubts,
Participants, if you have any doubts, you can write in the chat box. Otherwise, we will call it a day. Okay.
I think there is no question, sir.
Okay. So then that we will call a day. So tomorrow morning, exact what is the 9 o'clock we will start. Tomorrow I will able to discuss about what are the different types of sensors and what are the different types of activators which are going to be required for you in the mechatronics point of view. That will be somewhat interactive and that will be somewhat good understanding. So this modeling and simulation, it will be somewhat little bit mathematical thing, but if you understand it, it is going to be it is going to be more interesting what going to have. But tomorrow lecture we will able to have what are the different types of sensors and activators which are going to be mainly used in the mechatronic system. I will able to explain you starting from the basic sensors to what are the different types of sensors which we are going to be using in the latest industry 4.0. That type of sensors also I will able to discuss you, and some of the topics, research topics, what my research scholars are going to be doing, that also I will able to discuss you the tomorrow. So I will we will able to, if you have no doubts, then we will meet you tomorrow. Okay.
Dear participants, the feedback link is shared in the chat box. You can check.
Okay. So then if it is no doubts, then we will call it a day. Okay.
Okay,
So,
sir.
okay.